Okay, let me start the recording here. Okay, so motion in space, velocity and acceleration. Really, this is a very, how many have learned that, hey, velocity's the derivative of position, and acceleration's the derivative of velocity? How many have learned that? Okay, pretty much all of you. You've seen that in Calculus 1, for instance. That was, and you know, in multivariable calculus, we have an analogous situation. It's just with vectors. So, you know, in example 1 here, find the acceleration given position. You know, it's not a big deal. You know, you have a position vector, r of t equals t cubed I plus t squared j. Okay, you find the velocity by taking the derivative of position, and you get a velocity vector, and you find the acceleration vector by taking the derivative of velocity, which therefore would be the second derivative of position. Okay, so you get your acceleration and velocity vectors. And, you know, here's figure 2. Figure 2 for this problem. Well, hold on. I need to do a little bit more. They want you to find the velocity, speed, acceleration when t equals 1 and illustrate geometrically. Okay, no problem. So speed is the magnitude of velocity. And at t equals 1, they compute the velocity vector, the acceleration vector, and the speed at t equals 1. And then they have a little picture here where they have this space curve, r of t equals t cubed I plus t squared j. And they've drawn the velocity at when t equals 1, you're at the point 1, 1 on that space curve. The velocity vector appears to be what to the space curve in that picture in figure 2? The velocity vector appears to be what to the space curve? There's a key word I'm looking for here. Tangent. That's right, Robin. And that makes sense. That makes sense. Okay, because the velocity vector is the derivative of position, the derivative of r, and we learned before that r prime is tangent to r. Okay, so I mean that's really you know, one of the big ideas here, and of course there are other things that you can learn about here. Okay, example 3 deals with find position given acceleration from an integral sense. I'll let you look at that example. I want to get one example done before our class ends. I might go over a little bit, but you've seen this kind of thing where you integrate a vector, and then I'll let you look at example 3. But a thing I want to show you here is that in regards to, let me see, one moment, class. I want to find the example here. Sorry, let's get over here. Yeah, so tangential and normal components of acceleration, they show here that the here's what I wanted to show you, figure 7. Really, this section is really just a lot of it is just applying formulas. So I'm going to let you study it a little bit on your own. You'll be fine. But look here, they show that the acceleration vector is a linear combination of the tangent vectors and the normal vectors. Okay, the acceleration vector lies in the plane that contains the tangent vectors and the normal vectors. In other words, the acceleration vector lies in the osculating plane. And the acceleration vector, the weights on the tangent normal vectors are based on speed and or the derivative of speed, speed squared, and the curvature. So curvature is going to affect acceleration. Okay, how many have noticed that if you round a curve in your car quicker, your acceleration inward is more if you round a turn? How many have noticed that? Yeah, yeah, that's exactly right. The acceleration of the car goes inward, and you slide on the seat and hit the door, right? We don't want that, but all right. So, there's some cool stuff here, cool stuff. And I want to do a really cool example here with you. Let me give you a moment here and copy this example down. Okay, it's the spaceship problem. We got to do this spaceship problem. So let me give you a moment to copy this down, this example. Let's see. There's a comment here. Hold on. Okay, yeah. Right. G-forces, centripetal acceleration. So this example really, I think, demonstrates a lot. I mean, it covers some nice things about in section 10.4. I mean, we ought to do an applied problem dealing with, dealing with velocity. So in this problem, you're told that the position of function of a spaceship is given by this position vector. And the coordinates of a space station are at 6, 4, 9. The captain wants the spaceship to coast into the space station. Okay, in other words, when should the engines be turned off? How many recall the movie has Matt Damon in it? I think it's called Mars, where he needs to be rescued off of the Mars. And they have to time things right. Okay, DDF members. The Martian, okay, thank you. Ryan remembers, and Christopher. And I believe in that problem, they had to time the spaceship when to, I'm trying to recall, there was something they had to get the time right to pick up Matt Damon from Mars. He was going to jettison off of Mars. And so, this is kind of, I mean, I can see this as a very, I mean, that was a movie, but, the captain, why would the captain want the spaceship to coast into the space station? Why would he or she want that? Okay, Ryan, to reduce the force of impact. Also, less fuel, right? Lots of reasons. So, gas, there you go. There you go. So, I'm going to show you how to solve this problem. It's really a beautiful problem. May I go to the next page? Does everybody have it copied down? Okay, Ryan's good. Deodath's good. Okay, what would be helpful to start this problem off? It's worth 1,000 words. A picture. Good, and that's what I have here on the next page. I've drawn a picture, so of course, it's just a picture, you know, but frame of reference is, of course, the origin. And then you have the spaceship, hold on here. You have the spaceship, okay, that's going along this path. Okay, this is so the position vector is r of t. Okay, the position vector is r of t. And as the value of t changes, as time changes, the spaceship takes on new positions. New positions, okay, with respect to time. But what the pilot of the spaceship wants to do is at a certain time, he or she wants to turn his engines off and coast right into the space station. You see that this dashed line here. Coast. Let me maybe put it in green. Coast right into that space station located at coordinates 649. So at that point where the black dot is, that's the point where the pilot would have to turn off his engines or her engines. Okay. So, okay, well, that point on the space curve corresponds to some value of t. We want to find that value of t. So, in the picture, also now, there's another dashed line up here. There's another dashed line. And does it make sense that that vector would be equal to r of t plus some multiple c times v of t based on the picture, because that's important for the problem. Good, good, good. So, of course, v of t, the velocity vector, is equal, the velocity vector here is equal to this vector. But that vector, v of t, doesn't go all the way to the space station, okay? But if we take a multiple, as a matter of fact, how far does the vector v of t go to, based on the picture, just this little picture, and it's just, I'm just asking. I mean, I'm not even saying, this is just a symbolic representation, but hey, if the velocity vector v of t were that long, how far does it get? How far is it more to the space? Okay, it's halfway to the space station. So in that case, the constant c would be equal to 2, right? If you had r of t plus 2 times v, that would give you a vector. That would give you this yellow vector here that goes to the space station. This yellow vector up here. So this is really the key in solving this problem. So what we do is we have to compute then well, we have to compute the velocity vector. And then we recognize that for the spaceship to coast into the station, we need to find values for c and t such that r of t plus c times v of t, the velocity vector, equals 649. And of course, I took derivatives here, used the chain rule and so forth to get my velocity vector. All right, and now I think let me know when you're ready to move to the next page. Notice I use correct notation, vector symbols. Notation is very important. All right, Ryan's good. And you know, in real life for this kind of problem, you might, well, you know, to find C and T, you might use computers to find that. But nevertheless, how do you program the computers? You know, humans program the computers and they have to know their math. They have to know their calculus. So, all right, I'll go to the next page if we're good. Does anybody need more time? Okay, Robin's good. And maybe I get one more thumbs up and I'll move forward. Okay, how about two more thumbs up? Thank you, Deodath. I'd like to. Okay, John's good. All right, let's move forward. So we've got to make use of this vector equation here. We've got to make use of it. So, okay, here's the vector equation. And now what I'm doing is I'm substituting in the vectors. And this is going to give us then three equations that have to be true based on the geometry of the problem. These three equations have to be true. But how did I get those equations? How did I get those equations? So think on it a little bit. Well, the equations come, you know, my hint is look here. And remember, we have an equal sign here, we have an equal sign there. We have an equals. So if you're going to say a vector equals, I mean, we got here, we have here one vector we have one vector, and we're setting it equal to another vector. We're saying the one vector equals the other vector. So, okay, well, that means then that 3 plus t plus c has to equal 6. Where are we getting that from? 3 plus t plus c times 1. Let me do it here. 3 plus t plus c times 1 has to equal 6. The x coordinates, that's right, Marvelous, very good. If the vector on the left is going to equal 6, 4, 9, the vector on the right, the x components have to be equal. Similarly, 2 plus the log of t plus c times 1 over t has to equal 4. Oh, there's the second equation. And finally, for the z, that we did the y components there, the y components. Now we equate the z components. 7 minus 4 times t squared plus 1 plus c times 8t over t squared plus 1 squared equals 9. There's the third equation. Are we okay with these equations, how we got them? Does it make sense that based off of this, we equate the components? Okay, good. All right, does anybody have a question on that, or Deodath's comfortable, John's comfortable? Ryan's comfortable? I mean, this has to be true then. So, okay, we have how many variables in these equations? How many variables? 2 variables, c and t, and we have 3 equations. So, you know, hopefully it'll work out. So the first equation says that c is going to equal to 3 minus t. So the first equation, what I do is I solve that for c. C will equal 6 minus 3 minus t. So c equals 3 minus t. So then I can take that and substitute it in equation 3. Okay, I pick equation 3 because it's easier to substitute c in equation 3 than it is equation 2, because equation 2 has a log. So I wind up with this equation, and then I multiply both sides of this equation by the least common denominator, which is going to be t squared plus 1 quantity squared. Okay, that's t squared plus 1 quantity squared. Okay, this of course is over 1. So you do the math, and some things are going to simplify, and you're going to end up with this equation here. Okay, we're almost done. If you could stay a few extra minutes, I'd appreciate it. If you can, I understand. But if you, it'll be in the recording. But we get here. Are there any questions up to this step? Can we solve this equation for t, this big equation, this big polynomial equation? Absolutely. We can use a numerical solver, like how many might use Desmos to solve that? I've not solved those kind of things in Desmos, but does Desmos solve polynomial equations? Can it do that? You know, DES, Desmos. How many have used Desmos before? All right, or you could use your, okay, for graphing, sure. You could use your TI-84 calculator and bring this part over here, bring that over, and you'll have a polynomial equation equals 0, and then you can just find out where the zeros are. Yeah, you could. That I like that, Christopher. Christopher says, why not graph on your TI calculator or in Desmos? Graph this function. You could do it on your calculator. Graph this function on the left. Graph this function on the right, and see where they intersect. Use the intersect feature. Right, there you go. So you can do this. So we can solve for t. Yeah, absolutely. Not a problem. And so if we do that, then let me get to the answer. We're good? So everybody's good up to here? Are there any questions? Okay. Well, if you solve that, you're going to get t equals 1. That's what you're going to get. And so by the second equation, the second equation is the only one we haven't used yet. But now we know the value of c. C equals, if t is 1, c is going to be 3 minus 1, which is 2. And we know t is 1. So based on that, we do that just to confirm that t equals 1 is the solution. All to the second equation. All three equations have to be satisfied for this to work. And if c equals 2 and t equals 1, all three equations are satisfied. We utilize the first and third equation already, and then we found the value t equals 1 and c equals 2. Well, we just substitute those in the second equation, and hey, the second equation is satisfied. So indeed, t equals 1, whether it's 1 minute, 1 hour, or whatever. It's the correct time to turn those engines off. And of course, like I was saying, I'm sure the programs are done, programs are written for the computers on board spaceships and so forth, but somebody has to program the computers, and they have to know the math, they have to know the engineering and the physics and all that. So how many think this is a pretty cool problem? Yeah, John likes it. Diadath, Christopher, I agree, Christopher. Applications definitely are helpful. It's nice to see where things are used. It's very nice. And are there any questions at all? Okay, Diadath's comfortable. Ryan's comfortable. All right, well, I'll stop the recording then.